All right. Well, good evening. Thank you for taking some time out of your busy schedules to come and see my presentation. My name is Nikhil Chellam, and I am a student at Rice University, Rising Junior, and I'm pursuing a dual degree in chemical engineering and a degree in history as well. For the past 10 weeks, I've been working under Dr. Fazil Tafti in the Department of Physics, where I've been doing research on the thermoelectric properties of certain classes of wild semimetals that the lab has produced. But before I actually go into my research, I wish to present a scenario that can help further contextualize the rather esoteric nature of my research. So, picture this. You have a box. In that box, you have 50 red marbles and 50 green marbles. Those marbles are completely separated, so there's no mixing between the two. You then close that box, wait for maybe 30 seconds, then you open that box. For some weird reason now, you have 25 red marbles and 75 green marbles, yet the total amount of marbles remain the same. In this case, it might be due to some like weird black magic or something, but in these certain classes of wild semimetals, this phenomenon is actually governed by a very interesting case in quantum mechanics known as the chiral anomaly. And during my presentation, I wish to present my background and the goals of my research, and then the squeeze test, which is the kind of overarching test that I wish to apply throughout my project, then the results of the squeeze test and the methods used to apply that, and we applied it to two different materials. First being crystalline bismuth, which has been extensively studied, and so we can use this as a comparison or a control group. And then vanadium diarsenide, which has not been studied at all, and we wish to explore whether or not this effect exists in this material. So now I wish to go into the chiral anomaly. As Dr. Birch mentioned in his opening statements, particles can be classified based on their spin. You have spin up and you have spin down particles. Along with that, their handedness can also be defined by the right-hand rule, or in the case of electrons, the left-hand rule. We have left-handed particles, as in the category over here to the left. Then we have right-handed particles to the right. And in the presence of or in the absence, rather, of a magnetic field, known as the B field, we actually cause the total energy, or the Hamiltonian, of our system to kind of separate out into wild blocks with opposite chiralities. Chiralities refer to the left-handed nature or the right-handed nature of our particles. Once we have the presence of a strong magnetic field, we then have these wild states quantized into Landau levels, which is the quantized cyclotron motion, or the rotational motion experienced by these electrons once they're directed by a magnetic field. And these lowest Landau levels, or the areas highlighted in blue or in yellow, red, are chiral. Along with this, once you have a strong magnetic field, these electrons segregate into left and right movers. However, if we apply an electric field, or E field, parallel to our B field, it induces mixing between our left and right movers, as illustrated by this animation. So now, we don't see a conservation of our chiral current. We see an unequal proportion of our left-handed and our right-handed movers. And this violates the conservation of chiral charge density, one of is like a fundamental principle of quantum mechanics. And along with this, something very profound can be observed in this quantum mechanical phenomenon. As quantum mechanics is largely based on probability, you generally don't really see that many observables. In this case, however, we can see a large negative longitudinal, that is when the electric field is parallel to the magnetic field, magnetoresistance, which otherwise is defined as LMR. Magnetoresistance is defined as the percent change of our magnetic field compared to zero field with increasing resistance. However, we also see similar effects observed due to an extrinsic effect that results from a experimentation. In previous studies that actually falsely concluded that the chiral anomaly is observed in other materials such as tantalum arsenide, and that is actually due to current jetting effects. As we see in this figure over here, we have a localization of charge density along the center, and the charge density gets weaker and weaker and weaker once you get to the fringes of the sample. So because of that, once you have a stronger magnetic field, your charge density actually becomes more and more localized towards the center. And once you measure resistance, because you have a smaller charge density, you experience a smaller resistance because of Ohm's law, V equals IR. Because you have a smaller current, you therefore also have a smaller resistance. And that can also provide a confounding variable in your measurements that's also detected as a negative longitudinal magnetoresistance. Because of this, measurements of longitudinal resistivity are most vulnerable to the inhomogeneous flow that arises from current jetting effects. And so the goal of this project, therefore, is to separate these intrinsic chiral anomaly properties from the extrinsic current jetting effects in our LMR experiments. And we do that by applying the squeeze test. The squeeze test relies on the fundamental assumption that we will have current jetting effects prevalent. We focus our current density into a narrow beam with our material line parallel to the magnetic field. And we measure the voltage difference across the edge, or the yellow spots over here, and the spine, or the blue spots directly at the center of our material. Then we also attempted to keep our current contact diameter small in order to accentuate these current jetting effects. Because if we have our current contacts large enough, you actually start inducing, or you start allowing for the conductivity throughout your material to increase, and so you don't really experience the same level of inhomogeneity that you would express with a smaller contact signal. And if we see that our spines, the resistance across our spine and the resistance across our edge decrease with increasing magnetic field, it produces a confirmation that our longitudinal magnetoresistance is intrinsic. So over here, we actually see the LMR profile of crystalline bismuth as we found in the literature. Over here in the resistance across the spine, we see a V shape in which the resistance decreases and then increases with as field increases in magnitude. However, on the edge, we see a different pattern. We see a classic hat shape. The literature is also not able to provide any conclusive evidence for why we experience a cusp around zero field, but we still see the characteristic hat shape. And because bismuth has been extensively studied, and because we see a discrepancy across the resistance profile of the spine and the edge, we can confirm that the measurements arise from current jetting effects. That is, our bismuth is topologically trivial. However, we see the same profile in sodium-3 bismuth. We see the same characteristic hat shape. However, on the spine, we also see the same hat shape. That means we still experience a negative longitudinal magnetoresistance across both the spine and the edge. Whereas in crystalline bismuth, you don't see that in the spine. So that means any effects due to current jetting are very minimal compared to the strength of the chiral anomaly. However, we still see the effects due to the chiral anomaly present at high magnitude of our magnetic field, as evidenced by the slight upturn in the resistance at high field. However, any effects due to the chiral anomaly are rather superseded by the strengths by the chiral anomaly. Sorry, I meant to say the current jetting effects before. So, our methods actually involved applying our squeeze test to crystalline bismuth to kind of further confirm the study, and vanadium arsenide, which has not been studied before. In order to do that, we first deposited 5 nanometers of chromium and 45 nanometers of gold onto our material for our current contacts. We then positioned our wires ideally in this configuration in our silver paint to ensure contact. Additionally, for larger samples, that is our bismuth samples for the most part, we used a shadow mask that I developed using a PCB writer with the pore sizes 500 micrometer diameter. However, for smaller crystals, such as our vanadium diarsenide, we actually have to resort to smaller current contacts of 100 micrometers. Once we configured it properly, we then placed it into our quantum dynapool PPMS machine to obtain our LMR profile. Once we got our LMR profile for our raw data, we then interpolated between the points in order to get a kind of approximation as to the behavior of our LMR. And then once we interpolated, we then had to minimize any noise caused from the Hall effect, which is the production of a potential difference once our E field is not parallel to our B field. And thus doing so, it symmetrized our data, as you can see over here, compared to this. And then once we symmetrized it, we then converted our resistance to magnetoresistance, which is, as I said earlier, the percent change compared to zero field. So over here, we see in the case of bismuth, our first sample was a 3 millimeter by 3.5 millimeter size sample and a 0.6 millimeter thick. Over here on the x-axis, we have our magnetic field, and on the y-axis, on the top two panels, we have our resistance across the edge and spine, and on the bottom two panels, we have the magnetoresistance across the edge and the spine. However, over here on the edge, we can see the asymmetric effects that arise from the Hall effect. Over here, we see that the voltage contacts are not properly aligned, and that is, and so as a result, this gives evidence of why we need to actually symmetrize our data. Once we symmetrize our data, we then got a match that was on the edge was pretty similar to that we found in the literature. However, on the spine, we see large oscillations at large field for 1.8 and 20 Kelvin. So this suggests that our configuration of our sample is not ideal, and some other effects need to be adjusted for in order to improve the quality of our data. So our next sample, we then had we had the same dimensions, size and length and width, and we halved the thickness. Over here, we obtained a much cleaner sample. We still see the same results across the spine. However, in the edge, we now see a more similar results that match that of the literature. We see the characteristic hat shape. However, there are still some things that need to be improved. But we still see the negative longitudinal magnetoresistance observed at the edge. Next, we then standard it down again to 0.16 millimeters, so 1/4 the thickness of the previous sample. This is contacts appropriately, and lo and behold, we have a nearly identical LMR profile to that we found in the literature. We see the characteristic V shape in the in the spine, sorry. And in the edge, we see this very nice looking kind of sombrero shape in which at high magnitude field, it levels off asymptotically. And then around the middle, we see the characteristic cusp and like the peaks. So this suggests that multiple variables play in a role in our data collection. The configuration of our current, or the configuration of our current contacts and our voltage contacts need to be properly aligned such that we have like an equal kind of alignment between our spine and our voltage, or spine and edge voltage contacts. Along with that, we need to position our current contacts immediately across the edge and reduce our silver paint to prevent any sort of like charge density kind of being distributed more uniformly across our sample. And now we try to scale this down to more or less match the same dimensions of our business profile. We see similar results. However, at positive field, we actually start seeing like a little bit deviations from what we expect. And over here, we can actually see that it's probably due to the fact that we have a misalignment between the current contact, the voltage contacts across the edge of the spine. Disclaimer, you have to be very nimble in order to put these contacts on, so yeah. And additionally, we see that even small deviations from like alignment that you might not see in larger samples can have profound effects in smaller samples. This distance difference might not be that prevalent of an effect in larger samples. However, once we scale down our size, these effects become more and more prominent because now the distance from the edge of our sample now becomes more and more accentuated, proportional. So, but however, this actually provides evidence to suggest that our squeeze test can actually be applied to small samples. So now we actually apply this to vanadium diarsenide. In vanadium diarsenide, we had a 770 micrometer by 340 micrometer size sample and about 30 micrometer thick. And we see the characteristic V shape across the spine. And we see a slight kind of hat shape across the edge. And over here we still see negative LMR profile. However, it's at lower temperatures, same thing with the bismuth. And we can conclude, because we have a very small thickness, the configuration is close to ideal. We have our current contacts relatively small, and we also have like no overlap between the current contacts as well. That this suggests that the chiral anomaly is not present in vanadium diarsenide. Any sort of negative LMR arises solely from the fact that we have an uneven current density present throughout our sample. So with that in mind, I now present my acknowledgements. I would first like to thank the Tafty Lab for providing a fostering environment for educating me in the principles of quantum physics. I came into this program with barely any background in physics. Last time I taken a physics course was about 4 years ago. And under Dr. Tafty, I feel like I have grown not only as a researcher, but as an individual as well. I also like to thank Hong Yang, one of the grad students in our lab, for bearing with me as I hogged the PPMS machine basically the entire time, and for dealing with my sassy remarks. I'd also like to thank Nicola and Tom for being amazing lab members and for also coming to my presentation today. And yeah, so pretty much thank you for the Tapia Lab for providing me this opportunity. I'd also like to thank the National Science Foundation for this opportunity, for the funding in order to make my experience a great one. And finally, I would like to thank the administrators of the BC REU program for not only making this an educational experience, but also making this one fun and entertaining as well. Thank you.
Questions?
So you mentioned that you did this business at
Yes.
multiple times, and it seemed to have an effect on your data. Do you think that this was just because you had a fresh, clean surface on your crystal, or do you think the actual thickness plays a role in resistant pressure?
That's a good question, actually. I actually wanted to adjust that, but I didn't do my presentation due to time constraints. But actually, the principal reason as to why thickness plays a huge role in our electron density is because the thicker your sample, the more uneven your electron density is. You have rather than localizing it across your x and y dimensions, you now have to localize it among your z directions as well. So your thickness of your sample also plays an inherent role in governing the electron distribution throughout your material. By minimizing the gradient or the electron distribution through the material across the z-axis, you're then able to accentuate any kind of inhomogeneity due to current jetting effects across your edge of your spine. Does that sufficiently answer your question? Okay. Cameron?
I can't remember if you said this or not, but how did you actually cut your samples?
We cleaved it using a razor. But for vanadium diarsenide, it was very brittle. So what we had to actually do was, the first few times they were destroyed and we were sad. But afterwards we kind of just chose the samples that are closest to square. And any sort of like unevenness due to like the surface level like roughness or anything, we kind of we sanded it down using a very interesting method. We had like a brass tube, you had some wood resin, or you had some resin, which you melted that resin, you placed the crystal on top, and you sanded it over a wet paper towel, or over a wet piece of sandpaper, sorry, and then you kind of just like rolled around the brass tube. Does that sufficiently answer your question? Yeah. Okay. Any other questions? Yes, Sophie.
So earlier in the beginning of the presentation, you explained a real-world application of your question would be, how did 50 red marbles and 50 green marbles change into like 75 green marbles and 25 red marbles? Is there a way you could frame, like, what would be another metaphor to describe your research with the graphs? Like, could you frame your question with real-world applications, because I got a little lost in the beginning.
So if I'm interpreting this correctly, you're trying to understand what are some real-world ramifications of my research?
Yes.
So like I said earlier, the research that I'm doing is very esoteric. It's largely limited to academia. We actually just wanted to do an experiment on this because this is a quantum mechanical phenomenon that has effects in classical physics. So even on the classical scale, we can see the effects due to these like quantum non-conservation of chiral current. And in terms of like practical or in terms of like real-world applications, I'm not entirely sure of them. They largely have to do in the realm of spintronics, if I'm correct. But apart from that, not really anything else. Sorry, that's a little bit,
I'm sorry, but
dislike.
But are you focusing on how 25 marbles can go from red to green? Is that one of the questions you're trying to answer in the context of your studies?
Yes, we're trying to see if this phenomenon, or the non-conservation of chiral currents, can be observed in these topologically non-trivial materials. As we see in the cases of both bismuth and vanadium diarsenide, they're both topologically trivial, so you do not see this instance. However, in the literature, we see this evidence in, as I mentioned earlier, sodium-3 bismuth and in gadolinium platinum bismuth, two classes of topologically non-trivial d-radical semimetals.
Thank you.
Okay, that's all the time we have, so let's